Welcome to G Fun Facts Online. Today we are diving deep into a subject that bridges the gap between ancient alchemy and futuristic nanotechnology. We are talking about gold, but not the gold you wear on your finger or the gold bars locked away in vaults. We are talking about gold stripped down to its absolute limit. A single atomic layer, a material so new and so strange that it forces us to rewrite the textbooks on physics and chemistry. This is the story of Goldene. For thousands of years, gold has been the ultimate symbol of permanence. It does not rust, it does not tarnish, and it does not react. It is the noble metal. But it turns out, gold has been keeping a secret. When you peel away the bulk and isolate just one layer of atoms, gold stops being gold as we know it. It transforms from a passive, shiny metal into an active, dynamic semiconductor. It becomes a catalyst. It interacts with light in ways that seem impossible. This discovery, announced in the spring of 2024, is not just a scientific curiosity. It is the beginning of a new era in materials science, potentially unlocking everything from limitless green energy to new cures for cancer. To understand why Goldene is such a massive deal, we first need to look at the revolution that started 20 years ago with a material called graphene. In 2004, physicists isolated a single layer of carbon atoms from graphite. They found that when you confine a material to two dimensions, the laws of physics change. Electrons are forced into a flat land, where they behave in bizarre, hyper-efficient ways. Graphene was stronger than steel and more conductive than copper. It launched a gold rush for 2D materials. Scientists successfully made silicene from silicon and phosphorine from phosphorus. But the holy grail remained elusive. They wanted to make a 2D metal. This was considered the impossible frontier. You see, metals are fundamentally different from carbon. In graphite, the layers are held together by weak forces, making them easy to peel apart like a deck of cards. But in metals, the atoms are held together by a metallic bond, a communal sea of electrons that pulls everything into a tight, three-dimensional cluster. Metals do not want to be flat sheets. If you try to create a single layer of metal atoms, the surface energy is so high that the atoms will instantly snap back into a clump to stabilize themselves. It is like trying to flatten a drop of water into a sheet and asking it to stay that way without a container. For decades, physics said it couldn't be done. But a team at Linköping University in Sweden proved physics wrong. This discovery wasn't the result of a targeted hunt for Goldene. It was a classic case of scientific serendipity. Lars Holtman and Shun Kashiwaya were working with a specific class of conductive ceramics, known as max phases. These are layered materials that combine the toughness of ceramics with the conductivity of metals. They were interested in a material called titanium silicon carbide. Their goal was mundane. They just wanted to coat this ceramic with gold to create a better electrical contact for high-temperature uses. But when they heated this mixture to 670 degrees Celsius, something strange happened. The gold didn't just sit on top. It melted and diffused into the ceramic. It engaged in a game of atomic musical chairs. The gold atoms kicked out the silicon atoms inside the ceramic and took their place. The silicon migrated to the surface and was washed away, leaving the researchers with a new material, titanium gold carbide. They had accidentally trapped single layers of gold inside a ceramic sandwich. The gold was there, flat and monatomic, but it was imprisoned between layers of titanium and carbon. The challenge was now one of liberation. How do you remove the bread of a sandwich without destroying the delicate filling, especially when that filling is a single layer of atoms that desperately wants to crumble? Standard chemical etching was too harsh. Using hydrofluoric acid, which is the standard tool for this kind of work, would have destroyed the gold along with the titanium. The team hit a wall. The breakthrough came from an unlikely source, the history of Japanese craftsmanship. Shun Kashiwaya looked into ancient techniques used by Japanese blacksmiths to forge swords and decorate metalware. He rediscovered a chemical concoction known as Murakami's reagent. This is a mix of potassium ferrocyanide and potassium hydroxide. In metallurgy, it is used to etch grain boundaries in steel to reveal the microstructure. It had never been used to synthesize a 2D material before. The team hypothesized that this ancient reagent could gently etch away the titanium carbide layers while leaving the gold intact. But it wasn't as simple as mixing chemicals. The process turned out to be incredibly delicate, requiring months of trial and error. They discovered a critical nuance. Potassium ferrocyanide is sensitive to light. When exposed to light, it can degrade into cyanide, which dissolves gold. So to save the Goldene, the entire etching process had to be conducted in darkness. Imagine that. The creation of the most futuristic material on Earth required ancient sword-making chemistry performed in the dark. Furthermore, even if they freed the gold, it would naturally want to curl up like a scroll. To prevent this, they added a surfactant, a soap-like molecule called cysteine. The surfactant acted as a scaffold, attaching to the gold surface and holding the sheet flat in the liquid solution. After months of waiting for the gentle etching process to finish, they filtered the solution and peered through an electron microscope. Staring back at them were not clumps of gold, but sheets. Ultra-thin, transparent, hexagonal lattices of pure gold. Goldene had been born. Now, let us talk about the physics, because this is where things get truly mind-blowing. The most shocking property of Goldene is that it does not act like gold. In its bulk form, gold is one of the best conductors of electricity known to man because its electrons are delocalized and free to flow. However, when you constrain gold to a single atomic layer, you restrict the movement of those electrons. You introduce quantum confinement. The continuous energy bands that allow electrons to flow freely in 3D gold are broken up. Consequently, Goldene exhibits semiconducting properties. This is a monumental shift. It means Goldene has a band gap, an energy hurdle that electrons must jump over to conduct. This tunable conductivity is the foundation of all modern electronics, like transistors and chips. Bulk gold is useless for logic because it is just a wire, but Goldene could theoretically be used to build the processor itself. Furthermore, in a block of gold, every gold atom is surrounded by 12 other gold atoms. They are fully coordinated and chemically inert. This is why gold doesn't rust. But in Goldene, each atom is only surrounded by 6 neighbors in a flat, hexagonal ring. This leaves every atom with dangling bonds or unsaturated valencies. The atoms are chemically frustrated. They are desperate to bond with something. This transforms Goldene from a noble, inert material into a catalytic powerhouse. It becomes hyper-reactive. This reactivity opens up billion-dollar industries. Let's look at the applications. First, the green hydrogen revolution. The world is desperate for clean fuel. Hydrogen is the answer, but making it is currently dirty or expensive, often relying on platinum catalysts. Goldene could change the equation. Its hyperreactive surface makes it a potential electrocatalyst for water splitting, turning water into hydrogen and oxygen. Because Goldene is only 1 atom thick, every single atom is on the surface and doing work. You could theoretically achieve the catalytic activity of a 1 kilogram gold bar with just a few grams of Goldene. This efficiency democratizes gold, making it economically viable for mass production. Then there is carbon capture. Goldene's dangling bonds make it hungry for carbon dioxide. Preliminary research suggests Goldene could act as a highly efficient catalyst for converting CO2 into useful fuels, like ethanol or methane. Imagine industrial smokestacks fitted with Goldene filters that don't just catch CO2, but instantly convert it into fuel that can be reused. It closes the carbon loop. The applications extend to medicine as well. Bulk gold is biocompatible and safe for the body. Goldene, however, might be deadly to bacteria. The sharp edges and charge properties of 2D gold sheets can physically slice through bacterial membranes or disrupt their metabolic processes. Yet, because it is gold, it remains non-toxic to human cells. This could lead to a new class of mechanical antibiotics that bacteria cannot develop resistance against. There is also potential for photothermal cancer therapy. Goldene has intense optical properties known as surface plasmon resonance. It can concentrate light energy millions of times more effectively than bulk gold. If Goldene particles are injected into the bloodstream and targeted to a tumor, an infrared laser could be shown on the area. The Goldene would absorb that light and convert it into heat with near-perfect efficiency, cooking the cancer cells from the inside out without harming surrounding healthy tissue. Finally, we must consider the future of electronics. As silicon chips reach their physical limits and Moore's law slows down, manufacturers are looking for new semiconductors. Goldene offers a material that is conductive, ultra-thin, and flexible. It could lead to invisible circuits on glass, sensors woven into clothing that never corrode, or foldable phones that do not break their internal circuits. Of course, challenges remain. Currently, Goldene is made in test tubes, and the etching process takes up to 2 months. Scaling this to industrial levels will require accelerating the synthesis without destroying the delicate sheets. Scientists also need to figure out how to stabilize dry Goldene sheets on substrates like silicon wafers. But Goldene is just the beginning. The method used to create it, the intercalation and etching of max phases, is a blueprint. We can now look forward to iodine, platinine, and silverine. We are standing on the precipice of a new family of materials. The discovery of Goldene teaches us that even the most familiar materials harbor secrets. For 5,000 years we thought we knew everything there was to know about the yellow metal. We were wrong. By shaving gold down to its atomic soul, we have unlocked a new element entirely. The future isn't just bright. It is Goldene.